Excellent. Good morning. Thanks for the invitation to be here, and thank the conference organizers. It's a huge effort doing this, so thank you to everyone who's been involved. For those of you who haven't met me, I am Jonathan Crass. I'm the co-PI of iLocater with Justin Krepp. And I realized writing this talk that iLocater has been in development for nearly a decade now, which one means I'm getting old. Two, it means there's been a lot of people involved in the project to get us to where we are today, which is what I'm going to tell you about. But also I thought there's a lot of new people potentially in the audience. So I'm going to start with a bit of context about iLocater and where it fits in the broader EPRV landscape. Hopefully. So when we started working on iLocater, perhaps the monster in the room that's still the monster in the room is how to address stellar variability from a technical standpoint. This is a figure from the EPRV working group report that just kind of highlights those many underlying physical phenomena that drive stellar variability, many RV amplitudes, many different timescales. Many of these phenomena will give us asymmetries in the spectral lines that we're trying to measure. So the question is, can we build an instrument that can resolve those asymmetries in the spectral lines? And with high resolution and high signal to noise, this is what we were deciding in about 2014, 2015. These were the numbers we kind of adopted for technical requirements for building iLocater and trying to resolve these asymmetries. The way I like to think about this is if you can build an instrument that can resolve the spectral asymmetries and you build a data reduction pipeline, the exoplanets come out for free. Easy, right? So that is the context of iLocater. The question is, how do you get to that high resolution? And if we think about radial velocity precision as a contribution from stellar variability and your instrument system from your telescope through to your instrument, the instrument part is a combination of photon noise typically and instrument systematics. So that photon noise and instrument systematics, if we go to higher resolution, we're going to have fewer photons per resolution element. That's going to boost your signal to noise unless you go to longer exposure times. So do you go to a larger telescope aperture? Well, the challenge there in a seeing limited instrument is that there's a direct relation between telescope aperture and the size of your grating. So the bigger telescope, the bigger the grating. You can get smart with tricks, but the question was, well, do we have to just build a bigger instrument that can make bigger instrument volumes? You have modal noise in seeing limited instruments, and you have a telescope-dependent architecture. The last couple of decades have seen a huge change in ground-based astronomy. We now have routine near-infrared adaptive optics that works pretty reliably. And you can get this as a picture of a PSF from the Large Binocular Telescope, and you can see the adaptive secondary mirror there. It's got 672 correction elements. If you can use small single mode fibers, 6-micron fibers is what we're using in iLocater, can you couple that effectively to that point spread function from the AO system? If you can, there's a lot of benefits for single mode fiber fed spectrographs. They're compact, they're diffraction limited, they can be high resolution, and they don't have modal noise in a spatial sense. They do have some polarization noise, but it's one stable Gaussian output beam from the system. So that was the context with iLocater going, let's try and do this technological change using adaptive optics for EPRV. So Notre Dame, where the instrument is led from, is a partner in the Large Binocular Telescope. You can see here. So this is two 8.4 meter mirrors, both with adaptive secondaries for providing AO correction. We went from knowing that that was the instrument we were using to derive some instrument requirements, and these were based on follow-up for tests. So our instrument precision is sort of a 70 centimeter per second number. 60 centimeters of that is from photon noise, 40 centimeters is from instruments, and this is based on specific requirements for LBT and magnitudes of stars. The big photon noise driver is adaptive optics performance. How much light can you get into that single mode fiber really dominates that, just like the question for the previous speaker. And then the instrument systematics is for spectrograph design, detector, and thermal control. And we're in the near infrared for iLocater because that's a good fit for the adaptive optics performance. We'd love to go to visible. Visible light AO is not there yet. So it's kind of the niche of where we are with adaptive optics capabilities today. We also have goals for some fainter and brighter stars where we can do better or worse with the photon noise, which is driven by AO performance. I don't have a huge amount of time to go into this today, but we have a lengthy error budget that defines what's going on with the instrument. I want to highlight that box right there. Those are sort of terms that are specific to the single mode fiber that we've thought about. And this error budget and a lot of simulation work has really meant that we've thought and I sort of looked into a lot of rocks when designing the instrument to see what's there and try to optimize iLocater as an architecture for single mode fiber fed spectrographs. So a lot of terms there, happy to talk about it, and there's a couple of papers about it as well if you want to look at those. So the instrument itself operates in the near infrared, so 0.97 to 1.31 microns, and that's really driven by adaptive optics performance, and also the Y-band is a fairly clear band from telluric contamination. Our median resolution for the spectrograph is 190,000. We can be fed by both LBT beams. We're starting initially with the left-hand side. We have a fiber injection system for there. And on the right-hand side, we could do iLocater in the future or any of the other LBT instruments. So PEPSI is a high-resolution visible spectrograph stabilized to a few meters per second. So we could have visible and near-infrared spectra simultaneously. And we get high spatial resolution on sky. So our PSF is about 40 milliarc seconds on sky. So we can start resolving binaries, doing exciting science there, spatial mapping potentially as well. The instrument has 4 major modules: the fiber injection system, or the acquisition camera, the spectrograph system, the thermally stable cryostat system, and the Fabry-Perot-based Etalon. The calibration, the fiber injection system was commissioned at the LBT in 2019. And what you can see in the yellow box here is what we're still working on at the moment. So the fiber injection system was installed at the telescope in June 2019. This was a terrifying moment of a small blue box fitting in a very tight space on the instrument gallery. It fitted with about ½ an inch of clearance to spare. And Andrew Bechter, you can see he was in the video there. He was a graduate student working on this, and this was a key part of his thesis. He's now gone off into industry working on lasers and single mode fibers. The question always has been with single mode fiber fed instruments is how much light can you get into these single mode fibers? And this is a plot of absolute coupling efficiency, how much light we get into that fiber over time. These are just a couple of short snapshots of data. This is a 6.5 magnitude star, and we're getting between 35 and 40% coupling efficiency. We conservatively said we need 20% to do our science case. So we're well exceeding that, and there's a lot of optimization we can still do on this. This is preliminary. The question was, well, that's 6.5 magnitude. What about something fainter? So this is an M4 type star, a 13.5 R magnitude, and we're still getting between 20 and 25% with the AO system at the LBT. So it's really kind of allowing us to do some good science here with reasonable fiber coupling. The cryostat system that houses the spectrograph is always been a CAD rendering until the last couple of years. It's heavily based on the NEWID and HPF thermal control systems. They have a lot of heritage. They've been demonstrated well in the field. If we take the lid off that, we have a steel and aluminum vacuum chamber that's lined with multi-layer insulation on the inside of that vacuum chamber wall. We have a thermally stabilized aluminum radiation shield, and we have 12 control points that use the same control system as NEWID and HPF with 2 and 4 wire sensors to give us sort of verification of performance. The big difference from those instruments is we use cryocoolers for cooling rather than liquid nitrogen. And then the spectrograph sits inside there. In summer 2020, we got delivery of the vacuum chamber for iLocater, and we took the lid off it in summer 2021, given the restrictions on lab access and everything else. So this is a picture of 2 of the undergraduates who are working on that project in the summer, Matt and Alexa. They did a lot of work on fabricating the multi-layer insulation in the clean room at Notre Dame. And this is them over a course of many days laying out all of those layers and putting together. Thank you, Gumi, for documenting all of that in the HPF paper. It made our life a lot easier. Here is the picture of that integrated into the system. And then we've since moved all of the instrument to Ohio State. I switched positions over the last year. So this is a picture last Monday of the cryostat inside the clean room environment at OSU, and we're going through all of the electrical integration at the moment. The spectrograph is illuminated with 3 single mode fibers, SM980 fibers. We collimate onto an R6 shell grating, that collimator module you can see in green. We go onto an R6 and then we cross disperse. This is an all reflective design. We made that choice early on in the instrument design because we didn't want to worry about transmissive optics. We also worried a little bit about polarization. That is going to be a challenge for single mode fiber fit instruments. But we image onto an H4RG10 detector. This is coming from the Roman Space Telescope project. They've invested heavily in improving a lot of the ugly characteristics in near-infrared arrays. You asked Teledyne, can I buy those improvements? And they currently say no. So we asked NASA nicely if we could borrow one of these detectors, and they said yes, which was very nice of them to do. So we have an H4RG10. This spectrograph is 70 centimeters across. And I just want to keep that in mind as we talk about resolution. The instrument is made of Invar optomechanics and silicon optics. That is a choice for optical performance. We need to be diffraction limited, but also thermal stability. The spectral resolution, this is as expected to be delivered when we do the optical testing. We're not quite there yet, but we'll know it. The median is 190,000, and we're going up to very high resolutions. The way we can do that is because we have the large collecting area of the LBT. We'll see what happens when we do the optical testing to see where we sit, but we'll really kind of move forward. Last Monday, the spectrograph finally met the cryostat for the first time. It fits. I didn't screw up, which is always good to know. We're still waiting on gratings to come. They're coming in the next couple of months, but we're doing that for integration of the two pieces together. And very quickly, we are actually diffraction limited. We're better than lambda by 10, lambda by 12, end to end through the spectrograph. And that's important. Aberrations can be a real problem for these diffraction limited systems. I'm going to skip over the measurement precision. It's that 70 centimeters, but we can still do stuff on visible stars. G stars and stars, we will still be able to do a few meters per second on, we think. We'll continue integration during the spring, and hopefully we'll be at the LBT late 2023. We've done a lot of design work for iLocater to really try and optimize it as an architecture for diffraction-limited spectrographs. There's a lot of work gone into that, and hopefully that will prove out when we put this on Sky and test it in the next couple of years. The next steps. 1, data reduction pipeline. This is a pitch. I would love input from the community about how we should do that. We are a very lean team, and it's the next big challenge for us, so I'd love to talk to people about that this week. We also would love a solar telescope feed. That's, of course, funding dependent as always. But the architecture is there. It's well optimized. And with that, I'll say thank you to the NSF for funding us. And thank you all for listening.
Thank you. About the resolving power, 180,000 or 190,000, could there have been a trade-off, a little bit lower resolving power for a even better coupling efficiency?
You can always go higher. Going to the R6 grading has caused some very weird effects. If I go back to that, I can't show it, but that spectral resolving power has a huge range across it. And it's because of the obliquity of the R6 that we're looking at. We did a lot of trade studies on that one. This was where we ended up. We could always go back and change the grading if we want to tune that and tweak it. There's some capabilities in there, changing the line spacing if we want to do it. We tried to stay with commercial gradings and matching what we had there, and this was the best fit. I think you could go back if you were going to build this again and kind of trade that off better, but it was where we started with for the design here.